Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Alex Lopez-Vasquez with us today. Hello, Alex.
Hello, Frank. Thanks for the invitation.
Oh, yeah. Well, thank you so much for agreeing to talk about your very lovely article. It's a nice one. So we'll get into it here in a little bit. Alex, where are you located at?
So currently, I am a postdoc in Taipei, in Asia.
Okay.
So I started 1 year ago.
Okay.
I arrived to Taipei one year ago.
Okay. And you did your grad work in Mexico?
Exactly.
UNAM?
UNAM, exactly. In the Morelia.
Yeah.
In the Institute of Astronomy and Astrophysics.
Very cool. Very cool. Well, that's a little bit of a culture change going from Mexico to Taiwan a little bit there. Yeah.
Yes, exactly. It's very
Do they have?
it's different, but it's very exciting.
Very cool. Very good. Very good. And it is June. Well, it's my June 20th as we record this. This is my Tuesday, and this is Alex's Wednesday because we're over the date line there. So yeah, we are going. And Alex, what do you like to do for research?
So my research focused on the molecular outflows.
Mm-hmm.
So I have the two different ways. For the theoretical, my PhD, I developed a theoretical model. And in the postdoc positions, so I work with the observations, without observations and with this SMA observations.
Cool. So you're the proverbial double threat. You do both theory and observations, yeah? Very cool. Very cool. Very nice, Dr. Alex. And that is going to bring us to this very awesome APJ article. It's open access, people. It's the open access era. You can go get a copy for free. Go grab one. A disk wind driving the rotating molecular outflow in CB26. And Alex, take us away.
Okay, thanks, Frank. So in this article, so the idea is reported the rotation signature in the CB26. So the rotation velocity was reported for Leonhardt in 2009. But with these observations, the idea was to default a very specific analysis. Okay. So, for example, Leonhardt report the rotation velocity with a very specific height, but the difference in this paper we reported to the different heights.
Okay, I'm with you. Mm-hmm.
So if you can show the figure 1.
Sure. Got an intro. These were carried out at CB 2013 and figure 1, moment 0.
Exactly. The difference of the observations between the Leonhardt and our observations is the resolution.
Okay.
For the observations, is the highest resolution of the SMA is around 1 arcsecond.
Mm-hmm. Okay.
Taurus is the distance is around 140 parsecs. So there is high resolution, not very high, but it's high resolution. So in moment 0, you can see the structure of the molecular outflow.
Yes, definitely.
So we combined the two different observations, the molecular line observation,
okay,
and also the continuum emission.
Got it. Okay.
The continuum is a 1.3 millimeters. So in this image, you can see the continuum emission like a contours, black contours, sorry, white contours.
White contours, yep.
And the line emission in color is the color bar.
Okay, very good. I'm with you.
So also you can see that the outflow extends around 12 arcseconds.
Yeah, thereabouts.
That in physical units is around 2000 AUs.
Okay. Okay.
So in the moment 2 image, moment 1 image, sorry, is figure 2, please.
Sure. Owens Valley, figure 2, first moment. Okay.
This is moment 2. So The moment 2 corresponds to the velocity. Is the velocity of the gas.
Okay.
If you
Okay.
see the signatures of the possible rotation. So in the blue sheet, in the east side of the outflow, present the blue sheet velocities, while the west side present the red sheet velocities. The
Mhm.
difference is around 1 kilometer per second.
Okay. Mhm.
This gradient of the velocity is interpreted like a rotation
Okay. Yes.
velocity. So the dotted black lines
Yes.
perpendicular to the jet axis corresponds to the PV diagrams for our analyze, very specific analyze.
Uh-huh. Okay.
Measure different physical properties. So in the next figure,
Okay, I'm with you. Figure 2. We're already rolling into the results on the first moment, and ooh, there we go. Position velocity diagrams. Let's take a look at this globally. Okay.
yes, exactly. In this figure, you can see the position velocity diagrams perpendicular to the jet axis.
Uh-huh.
Also, these diagrams, we make these diagrams to the different heights, represented with the zeta in the figures, the labels. The label
Yes.
is so these position velocity diagrams, you can measure the different physical properties. For example, the cylindrical radius, the expansion velocity, the rotation velocity. So, for example, the rotation velocity, you looks like a ellipse. No, not ellipse.
Yeah. Yeah.
Two different points.
Uh-huh.
It's present this.
Depending on where you are.
For example, if the outflow is not rotating, the shape is one bullet and one bullet.
Right.
Rotation velocity present the inclination. This is a very strong evidence that the outflow is rotating.
Indeed. Very cool.
Exactly. If you can see that at different heights present this behavior. So also the expansion velocity, you can measure it because if these bullets is very close, so the expansion velocity along the line of sight is very small. The difference is that these bullets is separated. The expansion velocity in the radial direction on the line of sight is bigger.
Very cool.
So also in these PV diagrams, you can measure the cylindrical radius because in the it's the horizontal axis.
Uh-huh.
The radius is the distance to the jet axis.
Right.
As you see when the emission finish the emission to horizontal in the horizontal direction of the PV diagrams, you can measure this radius. This is a cylindrical radius of the molecular outflow.
Cool. Very cool. Very cool.
Exactly. So in the next figure.
Okay. I'm with you. Okay. Opening angles, theta, and figure 4. We got radius of the outflow. Okay.
In left panel, we show the cylindrical radius. This cylindrical radius is when the emission of the PV diagrams finish in the horizontal axis.
Yes.
So you can see that increase with the height, upper edge, and the upper edge decrease, but the error bars is huge. So this figure is similar to the several sources. For example, in Orion Source I, in HH30, similar behavior. Okay. When the height increase or the distance, the vertical distance to between this midplane until the cut increase, the radius increase too. Okay. Because present the different behaviors. For example, you can explain this radius like a parabola,
Okay. Mhm.
relation between the height with the radius, like a parabola equation, or like a conical shape,
Yeah. Mhm.
but two shapes in the molecular output.
Okay.
So in the right panel, show the opening angle. The opening angle was estimated with equation 1.
Let's go
When
back. Let's go back to equation 1. Let's take a look at that. There we go. So it's the angle between R and R sin. Okay, over Z. Okay.
the
Okay.
equation 1 say that the opening angle is the arctan. Sorry.
Uh-huh.
Okay, the opening angle
Sorry.
related height with the radius. So what estimated with a fixed radius? The fixed radius is the centrifugal radius.
Okay.
So this source is around 200 AUs.
Mhm.
So you estimate the radius, you have a centrifugal radius and the height, you decide what
Delta relative to Z. Okay.
you can estimate the opening angle.
Cool. Okay. Mhm.
So that the behavior that the opening angle decrease with the height. So we can explain like a different streamlines. Different streamline that this wind
Oh,
rises from the accretion disk,
okay.
follow a very specific streamline, and never chokes with the other streamline from rises of the disk of the accretion disk. So it's difficult to imagine with these images, but the different works explain like if you have the disk, the accretion disk,
Uh-huh.
this wind arises in the different radius or the different distance to the central star,
Yes.
and follow this streamline
Okay.
or follow the next streamline.
Okay.
But streamlines never chokes, don't present the internal chokes.
Okay. Good. I'm with you. Good. Mhm.
Exactly. So in the figure 5, the present in the left panel the expansion velocity.
Mm-hmm.
If we suppose that the outflow is a disk wind, it's a wind that launches from the disk. This is the shape like a parabola or conical shape,
Yes.
but present the expansion velocity.
Mm-hmm.
You can imagine like a ellipses that expanding in the radial direction.
Mhm.
So the expansion velocity corresponds to this
Okay.
velocity. So while the rotation velocity in the right panel
Oh, that's interesting. Yeah.
along the line of sight. If you remember, we were the moment 1 of the
Uh-huh. Figure 1.
outflow. So you can see the blue shifts and red shifts.
Mm-hmm.
The
Yeah.
gas presented blue shift and red shift behavior. So this is only quantify this behavior. Quantify the difference between the two velocities.
Okay. Mm-hmm. That makes sense. Relative to figure 2. Very good.
With these quantities,
Uh-huh.
the property like a radius
V root.
and with the kinematic property like a expansion velocity and rotation velocities, you can where this outflow is launched. If you, I explained that the outflow probably comes from the accretion disk. These quantities, you can estimate the launching radius where this outflow is launching in the accretion disk.
Yes.
With the equation 3, probably.
Let's go to equation 3. There we go. 3 is the temperature.
Oh, equation 4.
4, yes, the mass of the disk. There we go.
Oh, no, sorry, equation 5.
Equation 5, that's the mass of the disk. Equation 5, then
Yes.
it is the origin of the outflow, location of the outflow. Okay.
In equation 5, the Anderson and collaborators in 2003 present a model that the magnetohydrodynamical disk winds. that explain the outflows and jets like a magnetohydrodynamic diswinds. This magnetohydrodynamic diswinds corresponds that these objects is launched from the accretion disk. So following the opening, the
Opening angle.
no opening angle, the magnetic fields.
Okay.
Two lines. So you have the magnetic field associated with the central star and the disk, responsible to launching the radios and collimate this radio and driving these winds.
Okay.
So in this equation, you have everything. For example, the radius, the bar P infinite is the radius, the cylindrical radius that we measure this radius.
Okay.
Also, the velocities, the poloidal velocity and the toroidal velocity. The toroidal is the rotation velocity, the observed rotation velocity, while the poloidal velocity is like a velocity of expansion in the direction of the jet axis, and the contribution with the expansion velocity in the line of sight.
Cool. Okay.
So we can estimate this velocity. Sorry, we can measure this velocity, also measure the mass of the central star. So I would like to come back to this estimation.
Right.
But we can estimate the launching radius. In figure 8, you can see that this launching radius is between 10 to 40 AUs. So it's very typical with this winch model.
Okay.
So this is the physical and kinematic properties, but also estimate the other properties of the molecular outflow and the accretion disk. For example, the mass of the outflow, also in equation 2.
Equation 2, that's our mass of the outflow. That's NH2, yes.
When the mass of the outflow depends on the projected area on the plane of the sky, also depends on the distance to the source, and the flux and the abundances. Because the majority in the universe, the majority hydrogen. So if you can measure the abundance between the CO and the hydrogen, estimate the mass of the outflow. And this mass and the outflow mass obtained is around it's around 10 to minus 5 solar masses. That is very typical in molecular outflows. We expect that the molecular outflows presents mass between 10 minus 5, 10 minus 3 solar masses. So also estimate the mass of this with the continuum emission.
Right, because we have that, right.
Also, we can estimate the mass of the accretion disk. With the distance of the flux, we can estimate this. So also assume that the relation between the dust and the gas mass is around 100. We obtain that the mass of this is 0.03 solar masses. That this is very massive in comparison with the outflow. But it's so with these properties also estimate the mass of the central star. With the with the position velocity diagrams, you can fit like a Keplerian curve. If we suppose that the central mass and the disk present the Keplerian rotation, you can estimate the enclosed mass in the disk radius. In figure 7, probably. Yes, figure
7. Yeah, figure 7.
In figure 7, you can see the Keplerian velocity. This is a PV diagram along this midplane, and you can see the Keplerian behavior. Behavior of the disk. So also for the 10 sigma, fit the Keplerian rotation of the Keplerian,
Okay.
the Keplerian fit. The Keplerian fit, and we obtain is around 0.66 solar masses.
Okay.
So
Little one.
with these quantities, with these velocities, we can estimate the other properties, and we can compare the origin of the molecular outflow. For example, exist two different ways to explain the molecular outflow. One way is that the outflow is this launched directly from the accretion disk, and the other way is that this wind entering material of the molecular cloud.
Gotcha. Cool. I'm with you.
So with these properties, for example, with the mass of the outflow, with the velocities, we can estimate the different rates. For example, the angular momentum rate and the linear momentum rate.
Yep.
One.
Go with me. I think we got a lot of that in table 1. I think you froze on me.
Yes, exactly. In table 1 is like a summary of the quantities derived from this molecular outflow and the disk, like an outflow mass and this mass, and also the mass loss rate.
Right.
Mass loss rate, so estimate the dynamical time, the outflow,
right,
and obtain the mass loss rate. Also, the linear momentum rate use this dynamical time is around 500 AUs.
Yeah.
So with the rotation velocity, no, the linear. See, yes, is use the expansion velocity. The expansion velocity in the line of sight. And finally, the angular momentum rate use the rotation velocity and the mass loss rate.
Wow.
So quantities are consist that the molecular outflow arises in the disk in the accretion disk.
Yes. Very cool. This mass, 0.3. Yep.
Yes.
Oh, wow. Very cool.
Object of this paper is the main objective of this paper.
Beautiful. Beautiful work. Congratulations. Very nice. I love it. Very good. All right. Alex, thank you so much for walking us through your very awesome APJ article. And you touched on it a little bit. So let me go ahead and push on it a little bit. Where do you think we go from here, given this article? Is there additional observations that could be done, perhaps at different wavelengths to pick up? Is there additional theoretical work that could be done on the underlying model, harking back to your PhD thesis? And just sort of next steps. Where do you think we go over the next couple of years on this topic? Are there other systems besides CD26 that we could compare with?
Is analyze the other sources, because this sources is a very beautiful source, because the outflow is the inclination angle of this source is very small.
Yeah.
But the problem is the north hemisphere. So for the astronomy, the currently the best telescope is ALMA. And the location of this source, ALMA cannot observe this source. So analyze the other sources. Analyze in other sources or the similar sources, and compare with the different theoretical models. Probably develop a theoretical model with compare with observation.
Okay, cool. Very good. Very good. Well, I really look forward to seeing this topic develop over the next couple of years. So I'll look forward to seeing your future articles. Be very good.
Yes, exactly.
Yeah, great. Thank you once again, Alex, for walking us through your very lovely article on CV26. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.